let's consider a solitary charge, capital Q, that is sitting in free space. We know that when you have a mass of material like the earth, it has an effect on any other mass which is brought near it. In a similar way, any charge which is placed in free space or in a region will have an effect on any other charge which is brought into that region. For the purpose of simplicity, we will imagine that the charge capital Q here is fixed in space, and we have another charge, let's say charge small q, which is brought into the space near this larger charge. So at this particular distance seen here from the charge capital Q, the charge small q will experience some kind of a force, and assuming that the small charge q, small q, is positive, it will be a repulsive force. So the force being experienced will be in this direction. We also realize that I could shift this smaller charge, small q, anywhere in this region. So I could randomly move this charge anywhere in this region, and for each point in this region, this tiny charge, small q, would be influenced by a specific definite amount of force. So that means that we can define a region, around this larger charge capital Q, and every point in that region has a definite value of electrostatic force associated with it. The picture that we have built up so far gives us a working definition for the word field in physics. So what is a field? What do we mean by field? It is a region in space. Where each point in that space has a property associated with it. This property can be anything. It can be a force, it can be a temperature, it can be a mass. But in this particular case, we are dealing with each of these points having a unique value of electrostatic force applied on the small charge q placed at that point, which is why this is also known as an electric field. In earlier days, this was known as the field of force or force lines or lines of force. This is not exactly true, especially when we are dealing with magnetic fields. So let us stick to the correct terminology. These are not considered lines of force. They are simply called electrical field lines in the current terminology. So we see that any point in this space, if you link with a smaller charge, you can say that the force is being applied in a straight line outwards. In other words, I can imagine this electrical field as a collection of electrical field lines. So we have electrical field lines which are radiating from this charge capital Q. And the convention that we follow is that for positive charges, the radiation of these lines points outwards. So they are radiating outwards. Please note, nothing is physically moving on those lines. It is not as if the charge is emitting some kind of radiation, but we consider the orientation of these electrical field lines to be outwards in the case of positive charges. Conversely, if we are dealing with negative charges, so let's say we have a negative charge, we will say that the electrical field lines in this particular case are oriented inwards. So in this case, again, we have radial straight lines, and the orientation of the electrical field for a negative charge. So this is a positive charge. Let's say this is a negative charge, negative Q. The electrical field lines will be oriented inwards. So what is the reason that we follow this convention, that the positive electrical field lines radiate outwards from the charge while the negative field lines radiate towards the charge? The reason for this is that we consider both of these electrical field line distributions in the context of a tiny positive charge placed in these regions. So if you place a positive charge in the vicinity of a larger positive charge, you will see that the force on this charge is oriented in the outward direction. While if you are considering a negative charge placed at the center of the system, the test charge will be experiencing an inward force. That is what we use to define the orientation of electrical field lines for positive and negative charges. Now, we could assign a number to the number of lines that are originating from this particular charge or going into a particular negative charge. Even though that is not entirely accurate, it still gives us a way to visualize the total effect that a particular charge is having in any given region. So, if we were to enclose these charges inside a region, you will note that since the charges are point charges and they are equally letting out or bringing in field lines from every direction, both of these charges are displaying what we call a spherical symmetry. We can enclose them in perfectly spherical volumes. And later on in the subsequent lessons, you will realize that spherical symmetry or any kind of symmetry greatly eases the problem of calculating the properties of these charges. We shall see this in subsequent lessons. For now, let us try to understand how we can link the concept of electrical field with the concept of electrical flux. Let's see how to do that. So, you already know the meaning of a plane angle or the definition of a plane angle. It is the ratio of an arc length to a radius. We can take this concept into 3 dimensions with the concept of the solid angle. A solid angle is equal to the ratio of the area of a projected region to the square of the radius connecting that region to the point of reference. Now, the reason the solid angle is so useful to us is because it helps us to visualize how electrical field lines are coming out or going into a point charge. For example, consider a watermelon. If you were to take out a conical slice out of that watermelon, there would be some value of surface area, that is the outer skin of that watermelon slice, and there would also be the radius of that watermelon, how deep you have cut inside the watermelon. So, you can see in this image that we have converted that into a diagram. Imagine that at the center of this spherical watermelon, there was a charge Q. So, this charge Q is a positive charge. It is radiating, as you can see, it is radiating electrical field lines in all directions. We are not considering the complete radiation of these electrical field lines just for this narrow slice that we have cut out of it. Now, this slice has 2 regions. As you can see, there is a larger region surrounding the point P2. P2 is a point and there is a region surrounding P2. There is also a point P1 and that point is surrounded by a smaller region that you can see here. So, here is our smaller region. So, we know the definition of the solid angle. It is denoted by the symbol capital omega and it is equal to the surface area or the area of the external surface, the surface area divided by the square of the radius. To understand what we mean by this, consider this slice of the watermelon. So, here is the center, this is the outer surface and this surface is at a radius R2 equal to OP2 from the center of this volume. So, this will be our radius. If I want to know what is the solid angle here, we get the value omega is equal to the surface area of this larger region. So, that will be S2, we can call this region S2 divided by the square of the radius R2. Also, in the same vein, if I want to find out the solid angle for the smaller region that is given here around P1, let's call that region, let's call this region S1. So, again we can calculate the solid angle for this. S1 will be divided by R1 square. So, R1 is equal to OP1. You will notice if you were to actually perform this experiment with a real watermelon, you would notice that both of these ratios come out to be perfectly equal. Because even though the surface area for the second region is larger, the radius is also larger. So, the ratio of the two quantities remains the same. Now notice what is happening with the electrical field lines. As these field lines are radiating outwards, you will notice that the density of the electrical field lines is much greater in the smaller area. You have a lot of field lines which are very close to each other. On the other hand, by the time they get to the second region, that is S2, the distance between the field lines has greatly increased. The field has become more diffuse. And you will notice that this increase in the diffusion of these field lines is because of the increased radius. As the radius keeps on increasing, the field lines become more and more farther apart. This clues us in as to why the electrostatic force is an inverse square force. Remember, the force exerted on any charge, that is F, is equal to the electrical field multiplied by the charge in that region. Now, the electrical field is weakening due to the increase in radius by the square of the radius. So, that tells us that the force on the charge will also decrease by the square of the radius or the square of the distance from the central charge or the reference charge. So, this gives us a visual idea of why electrostatic forces have the inverse square dependency. There are a few more properties that we need to discuss for electrical field lines. For example, in our convention, electrical field lines start at positive charges and terminate at negative charges. Second, the electrical field lines are smoothly flowing curves without any breaks or discontinuities, as long as there is no charge in the intervening region. So, you cannot have an electrical field line which is cutting off a 90-degree corner. That does not happen. The flow is always smooth in the form of a curve, as long as the region does not contain any other charges. Next, electrical field lines cannot cross each other. Now think about it. If two electrical field lines are crossing each other, that would mean that if you place a charge at the point of that intersection, it is under the influence of two different forces at the same time, which would resolve into a single resultant force, which means that we could visualize a single electrical field line there. This means that in reality, electrical field lines can never cross each other, because it would mean that the same charge was under the influence of two different lines at the same time, which is not possible. And lastly, we have to realize that electrical fields do not form continuous loops for electrostatic cases. This means that the electrical field will not form a closed loop without beginning or end. Magnetic fields can form closed loops in static cases, but for electrostatic situations, electrical field lines will not form a closed loop. They will only have a starting point at a positive charge and a termination point at a negative charge. We will understand how electrical fields and fluxes develop for various distributions of charges in subsequent lessons.
Manorama Horizon. Learning made simple.